second revision lesson on movement, but it's dealing with specifically how force affects movement in terms of the acceleration. Now, what I'd like you all to bear in mind throughout the whole of this is that if a force is acting on an object, then you must assume that it is changing its speed, it is accelerating. Now that could be either picking up speed or decreasing speed, but nonetheless it will change its speed. And this is all in accordance with an equation in which we have, I'm just going to set it out here, force is mass times acceleration. In other words, that the larger the force you apply, the greater the acceleration. But if you have a larger mass, then obviously the less the acceleration. Mass is measured in kilograms. Acceleration is measured in meters per second squared, as you've known before, and force, you know, is measured in newtons. Put together into a triangle if you need one, then this is how it sits together. But when I say force here, I mean as well a resultant force, because you might have more than one force acting on the object. And if there are more than one force acting, we're looking at the resultant force that causes this acceleration. Let's take, for example, a car, my badly drawn car, and let's show you how this resultant force manifests itself. Let's imagine you start accelerating from rest. The engines produce a certain force on the car. Well, because there's no other forces acting horizontally, I know there's some acting from the ground up and at its weight, but horizontally, the resultant force is rather large. And if there's a resultant force, we have said there's an acceleration. Okay, let's take position number 2. It's now been moving for a little bit of time. It's picked up some speed. We've still got the same driving force in the engine, but this time some drag has appeared. Let's call this one the engine. And this time a bit of drag has appeared. So now, when I look at the engine and the drag, the resultant force, of course, is smaller. But nonetheless, there is a resultant force, so we can say again that that is actually accelerating in that situation. Okay, let's imagine the car's gone a little bit further, and the air resistance has built up. The engine is driving it forwards, but now the drag is of equal size. So when we compare both of them, the resultant force is actually 0 horizontally. And that means the acceleration is 0, which means the velocity is constant. And that's a really, really important point. If the forces are balanced or there's no resultant force, then you're moving at a constant velocity. Right, what happens when you take your foot off the accelerator a little bit later on down the road? Well, at that speed, you still have the large drag force, but now you've taken your foot off the accelerator, so you get this huge resultant force acting backwards. And so therefore, what does that cause? Well, it doesn't suddenly move backwards, because actually it was moving in this direction in the first place. So you get a large de-acceleration happening on the object. Right, let's imagine we put some sums to this. Now you've got the concept of this idea of resultant force. Let's imagine we put some sums to it. Let's give you 2 examples which should be fast to work through. The first one is what would happen if we had a 1,200 kilogram object, probably a car, and it's accelerating at 5 meters per second squared. What's the force required in order to provide that acceleration? If you think you know, hit pause. Otherwise, here comes the solution. Okay, F equals ma, which is 1200 times 5, mass times acceleration, which gives me 6,000 newtons. Straightforward. What about the second one? Slight rearrangement needed here. Let's imagine I have 200 newtons as a resultant force on a 4 kilogram object. What's the resultant acceleration there? If you think you know, hit pause. Here comes the solution. Sorry, it's so cramped here, however. Right, we have F equals ma, of course, but now we're looking for the acceleration. So cover up A. Therefore, acceleration is F over m. which gives us 200 over 5 meters per second squared. Please write the seconds squared in there, so many people forget. Okay, so you've got an idea of the concept of resultant forces. You can do the maths. Let's look at one other example of how forces build, and that's with a skydiver. Lots of misconceptions here. Let's imagine the skydiver just jumps out of the aeroplane. The force acting on him is weight, but there's no drag, he's just jumped out. So therefore there's a significant resultant force. So this is accelerating. We're going to do exactly the same as we did with the car. Look at it a little later on. Still the same weight. That doesn't change like it could change with a car. This time there's a little bit of drag on there. So it's accelerating, but because the resultant force is obviously slightly smaller than it were in this case, it's accelerating not quite as much, a little less. Right, here comes the next situation where the drag force has actually become the same size as the weight, and so therefore the resultant force is 0. Therefore we're going, so the acceleration must be 0, so therefore we're going at a constant speed or constant velocity, or a terminal velocity. With skydivers it's approximately about 50 meters per second, that's about 150 miles per hour. Okay, then the parachute is opened. And because there's a much greater surface area of the parachute, suddenly the drag force at that speed is significant. The weight still stays the same. So now, therefore, our resultant force is actually going to be much larger than that, but it's upward quite significantly. So what happens here? Well, there is a de-acceleration. And then finally, because there's a de-acceleration, the parachutist starts to slow down, and when they slow down, so the drag force starts to reduce until it reaches the same size as the weight again, so the resultant force is 0, acceleration is 0, so therefore you get to the next constant speed, or your second terminal velocity. Okay, let's look at what that would look like on a velocity time graph. Okay, let's label these 1, 2, 3, situation 4, and 5. So initially we have a large acceleration on a velocity time graph. Steeper it is, the greater the acceleration. Number 2, it's slightly getting less. Number 3, it's at a constant speed, which we know is a flat line. So therefore that is the velocity time graph for the first 3 bits. 1, 2, 3. Suddenly we get a massive de-acceleration, so therefore, bang, de-acceleration is negative. It goes down, negative acceleration. And then we reach our second speed, terminal velocity, until you hit the ground. Bump. Okay, so actually this whole second topic is quite interlinked with the first, of course, because it's dealing with acceleration, but force is dealing with the acceleration. It's going to be a lot of describing. It's not, other than the first topic here, it's not going to be much number work, but you're going to have to describe the idea of resultant forces. So resultant forces. Then talk very carefully about accelerating or de-accelerating, and then using this idea of terminal velocity. And why does this drag force start increasing? Well, because it's moving faster or not. Okay, so short but sharp. Hope that made sense. That finishes motion.